All right, welcome. Your last assignment has been submitted. I've graded everything except for that last assignment, including the quizzes that I just handed back for those of you who wrote yes in the margins, your homework assignments, and so on. So the last thing on your to-do list for the course then is the final exam. And remember that you can prepare an equation sheet that's one page front and back, although I can't think really of any, well, I guess, yeah, the NRCS rainfall runoff relationship. So maybe there are a few things you want to put on that equation sheet. We're going to have our exam on Tuesday the 12th at 8 a.m., bright and early. All right, so today we're going to be talking about groundwater, and as I alluded in our last lecture, this is a really complicated topic, and I give it to you just sort of as a taste and so that you can get a feel for what's out there and the most basic groundwater flow equations, because sometimes those do pop up on the FE exam. But before we do that, just this morning I got the password so that we could take a look at the Flo2D results that Maricopa County has got on their website. And so let's launch the viewer, and it's pretty interesting. We'll be exploring this together. Since I just got the password about 30 minutes ago, I haven't had a chance to really get to the bottom of all the capabilities. And I saw it on Friday, so I've seen it, but let's have a look. As I mentioned last time, one of the astonishing things that they do is they contract with surveyors who have drones, and they'll fly an area using LiDAR, which is a technology that can produce really high resolution elevation data, and they take their own like aerial photography to have pictures in the background available. So here right now it looks like we've got the 100-year 24-hour storm set, and if we zoom in on this area, you can see what the depths are going to be under the peak discharge. And so I imagine that as we zoom in, it's maybe going to improve the quality of that raster, and we might be able to turn on some base layers that includes like where the roads are, and we could switch on some of the images too, help us see where the houses are. There we go. All right, so this is really high resolution stuff. I mean, you're seeing like where individual trees and bushes are, and so with this map you could find out, you know, if a tree that you're going to be planting is at risk of being washed away by the 100-year storm. And now obviously they're not doing it because they're worried about trees, they're worried about high-value real estate. And so here is a neighborhood, and the cool thing about this model, as it was described to me last weekend, is that you can do both rural areas and urban areas together, and there's kind of like a seamless transition between the two. And the HEC1 models that we've been setting up using WMS, that is principally, the strength of that is for rural areas or for undeveloped parts. You can put together a HEC1 model for a developed area, but you'd need to have it be exclusively developed. You know, blending the two in one model, having both a developed portion and an undeveloped portion, really doesn't work together that great. And so what we did in this class for urban watersheds was I showed you very briefly how to use Bentley StormCAD. And so remember, with StormCAD is where you're setting up inlets and sizing the pipes using the rational method, and you defined catchments, and there's some more sophisticated functionality there where you can also create curb and drain networks, and so you could see how deep the water is in the curb alongside of the road, and so it's got the open channel leading to the inlet and then water flowing through the pipe. But here, rather than having your urban being one model and your rural being another, it's seamlessly integrated together. And so they have to sometimes go in and add break lines so that, you know, maybe the elevation data would have had the flow going in a different direction, but they know that you know, because here's the road and the curbs are going to be directing the flow along that sheet towards certain inlets, or you know, as short as this road may be, it's possible that there isn't a separate storm sewer, but rather they just have the curbs that discharge directly to like an existing gully, kind of an idea. And so I'm going to have to play with this more over the coming days rather than grade your exams and all that sort of thing. But we can switch it over to, I guess it's mostly 100-year model. I thought that they had other return period storms besides that, but that's probably the sort of thing that I have to. Okay, so this is how transparent it is in case you don't want it to overtake some of the other things you're looking at. And the images are also can be made transparent. Pretty cool. So this is separate from the FEMA 100-year flood maps. You know, the 100-year flood maps that FEMA does are just sort of you're in or you're out of the floodplain. You know, this is showing you precisely where the water's going to be and what the depth of the water is going to be. So FEMA is kind of a binary thing: floodplain, no floodplain. Let's switch on some of this other stuff to see what we can see. Velocities, so that you have an idea of what the scour might be. So it looks like relatively low velocities through this neighborhood, and as we get further into the network where you have a lot more accumulation, then of course the scour velocities are going to increase, and that's also taking into account the slope of the channel. So I guess the warmer colors are indicating faster moving flow, and so this region with the faster velocities is going to have some scour potential. And so if you were putting in a culvert, or if you're building a bridge and you're thinking about the foundation of the bridge structure, then scour is going to be a risk at these locations where there's a higher maximum velocity. So that's pretty interesting stuff. So I'm just exploring this for the first time, and time of peak discharge, I think, is pretty interesting, because I guess this time of peak discharge is telling you how long you've got until the flow arrives at a certain location. And you know, that's significant because they have a couple of locations where every year they're putting in 2 more signs that can be remotely activated, or in some cases it detects flow in a stream, because they don't have culverts and bridges over every crossing. Sometimes the road just goes down and then it'll be momentarily flooded during a peak event and people just have to not drive across that road. But if it's at night, you can't really see how deep the water is, and sometimes people aren't paying attention, so they have flashing signals. And so this time of peak discharge is a useful bit of information, because it tells you a little bit how much lead time you've got from when it begins to rain to when that flow may be going through a crossing, and how reactive you've got to be before you activate a signal and the flow actually could be there. So that's, I mean, this model is amazing, and it's just light years beyond the capacities of HEC 1, so I think I've got my work cut out for me. I need to start adapting these same kind of models for West Virginia and learn more about Flo2D. It's not anything that I've used before, but they convinced me it's the wave of the future, and it's really a cool resource that they've put online. If any of you are interested in having access to the system, just to show to other people or maybe to look for yourself, then I can put you in touch with the people who can generate the passwords, because each user is supposed to have their own password for accessing the site. Well, high-resolution elevation mapping is one of the most important things. And then another thing that they showed me while I was there is that they have really detailed soil information as well. Like a really clear understanding of the soil that's in the watershed, particularly because in these areas they lose a lot of water during a storm. It's called transmission losses, where the water is infiltrating down into the channel. And I think the transmission losses are probably less of an issue here in West Virginia, but the point is that you need high-resolution elevation data, high-resolution soil type data. And I don't know that we have that same really detailed understanding of the soil properties on a wide-scale basis like they do across their county. I mean, they've commissioned some really exhaustive studies, and you think sand is sand, gravel is gravel, but it turns out that it's a lot more sophisticated than that. But I mean, there's a lot I still need to learn, so I would imagine that next year's version of hydrology is going to hopefully include a little bit of Flo2D, but I still have to iron out all the licensing issues and see if it's the sort of thing where in a lecture or two you can put something together meaningfully. I can make a HEC1 model in 10 minutes, but I don't know if I could make a Flo2D model in 10 minutes. In the absence of lots of data about a watershed, you can put together a HEC1 model on some assumptions kind of to give you like the envelope of possibilities, to say here's the worst case scenario, here's the best case scenario, and reality is somewhere in between. So it's not that it's useless, but this is a great resource and I'm anxious to start using it. All right, so the bulk of what we're going to be doing today is talking about groundwater. So groundwater hydrology includes how much water there is under the earth, different aspects of its quality, and that can include contamination from surface sources, like when there are spills, unintentional spills, or through the 40s and 50s, unfortunately, there were a lot of places where hazardous chemicals were land applied, and things like dry cleaning fluid or maybe explosive residues were just dumped into trenches, and then the trenches were covered with soil, and then over time that contamination seeped down into the water. So that's one aspect of quality, but another one that's really important is the infiltration of saline groundwater into previously freshwater aquifers. And that happens a lot in coastal areas and actually in inland areas as well, where there are brackish waters that, because you're pumping fresh water, the brackish waters start to intrude in areas that previously were freshwater. Trying to figure out where the water is and how it moves through the soil. So all of these concerns are addressed by the field of groundwater hydrology. And a big component of being able to predict these things is putting together models of where the water is and how it moves. And so just like there's WMS for surface water hydrology, the Aquifer people put together a program called GMS that's for groundwater flow. And it uses some of the principles we're going to be talking about today. Using the ground as a storage system for surface water with injection of stormwater is getting increasing attention as a technique for trying to prevent the reduction and depletion of aquifers. And in fact, down in Southern California, they're starting to use injection of treated wastewater and injection of desalinated water to try and prevent a coastal intrusion of salt water from the sea into freshwater aquifers. All right, so if we think about where the water on planet Earth is, the majority of it's in the oceans. And when we talked about the abundance of water in the context of surface water, we were saying that it's such a small fraction of the overall quantity of water that's available on Earth. And you see that compared to water that is in lakes and in streams, groundwater there's a lot more groundwater. Now much of it is greater than 1 kilometer deep, and the problem with that is it's not economically feasible to pump it out when it's that deep. Drilling a well that's 1,000 meters would be very costly, and then the expense of pumping is another issue. And so we're going to be focusing mostly on groundwater that's relatively close to the surface. There are a couple of videos here that we're going to watch just because it introduces some of the important concerns that exist with respect to groundwater. Okay, so what's your reaction to that video clip? Do you think they're going to be able to do it? They said their goal is to reduce the amount of water that's being consumed by 20% within 5 years. Right, okay. Yeah, so if you look at how they're using the water, they've got those big pivot irrigators that's spraying water from above. And so what would be an innovation you think that might be able to save water compared to that? Drip irrigation? What's the advantage of drip irrigation compared to spray irrigation? Okay, evaporation, yeah. And so when you have a small size droplet, you have a lot of surface area compared to the volume of the water that's there. And remember, evaporation is partly, a large part of evaporation is driven by the surface area that's available for the exchange from the liquid phase to the gas phase. And so, the evaporation calculations that we did was a free surface of a lake. And so, the area of water is the plan view of the area of whatever the lake is. But in the case of a droplet that's being sprayed from those pivot irrigators, by the time the droplet gets from the irrigator down to the ground, there's a good chance that an enormous fraction of that water has actually evaporated into the dry Kansas air, and it does no good to the plants that are there. So certainly putting a drip irrigator close to the root structure of the plant would be a big improvement, but of course it's a lot more expensive to think about for a cornfield. All of the plastic tubing that would have to go through the root structure of each row of the crop, it would be more costly than the value of the crop that's being grown. And so they can do drip irrigation for tomatoes because tomatoes are a high value thing. A good juicy tomato, if you go to the grocery store, is maybe going to cost you 50 cents or 75 cents just for the one tomato. But corn and soybeans and sorghum are relatively inexpensive crops that really they should be irrigated by rainfall, but in places that now the climate is drying up a little bit, they have to instead use water from the aquifer. Any other comments or thoughts about that? So I want you to think just for a moment before we move on to the next video that the water is a natural resource. Now, who owns it? There's water down in the ground, and these farmers can pump out as much as they want. There's no restrictions. Whoever has the biggest pump gets to take the most water. And so it's kind of interesting if you think about it, it's this natural resource, and I don't know, it could be argued it's a public resource, the clouds, the water coming from the sky. A lot of things that come from the sky we think of as a public resource, like, for instance, the radio frequencies that cell phone companies use to transmit messages. They have to pay to use that spectrum. They have to pay the government in auctions, and so they pay for the right to use that natural resource, which is the radio frequency spectrum. And so I think it would be interesting if the value of the resource that's being consumed had to be included in the price of the good that's being sold on the market. What if you had to pay even a small fee related to the water that's extracted from the ground, and you incorporate that into the cost of the corn or the rice or whatever is being sold, then that might provide the incentives to conserve. Because right now there is no incentive to conserve. Not a short-term incentive, and people respond very poorly to long-term threats. Like the long-term threat that each one of us faces is death, right? And how do we respond to that? We eat Cheetos, we drink Mountain Dew, we eat hot dogs, and we know those things are terrible for our health. But that's a long-term threat. That's not a today threat. Like if there was a short-term threat, poison in a glass in front of you, you'd run away from it. But the long-term threats are easy to ignore. And in the same way, this is the short-term threat for these people is I want to maximize my yields. And the long-term issue is, well, maybe in 10 or 20 years I won't have enough pumps to get the water out of the aquifer anymore, but I'll let me in the future worry about that. So sometimes people need to be guided through incentives to making decisions that are good in the long term by inducing a little bit of short-term pain to force people to conserve. Now, that's a political issue, and I don't suppose that there would be a lot of enthusiasm in conservative areas like Kansas for adopting like a water tax, but in the absence of something like that, I feel very confident that their conservation efforts will fail. That the 20% reduction in 5 years is never going to happen. And I'd bet my fortune on it. I'd bet my Bitcoin fortune on it. All right, well, let's watch the next video with that somber proclamation from your pessimist professor. I don't know how they expect us to study with the Christmas carols chiming in the background. It's a little distracting, right? All right, well, let's break this down. Someone drilled a hole in a field, and they put a pipe, like a well casing, and water is trickling into the hole. So did you understand what's the point of this hole that they drilled? What are they trying to encourage? Groundwater infiltration. They're trying to take the water from this pond and get it down underground where actually it could be stored. Because when it's in this pond, remember, it's subject to evaporation. This is a prime breeding ground for mosquitoes. And India is now a Zika country, especially in the south. Tamil Nadu is in the south of India. And so this is a health risk, and it's a lost resource if that water evaporates. And so just drilling a hole and encouraging the runoff from that field to go down underground is a great idea. And part of the purpose of this casing is, I would imagine, we can't see, but I would imagine it's slotted so that there are fine, it's like a mesh at the bottom to try and filter out any rocks or contamination that maybe would get down into, plug the holes as the water gets in. So this may require some occasional maintenance. Another thing that's relevant about this is in this field, the runoff from the surrounding land is all going to this pool area here, and it's going to bring fine sediments with it. And so those fine sediments are going to be clogging the soil pores at the surface. And so there probably isn't good surface infiltration down into the ground because over the long term, the sediments have clogged that. Whereas in this well casing, you also have quite a bit of hydrostatic head pushing the water down into the aquifer. If you think about the water that's draining into here, instead of just 3 or 4 inches at the surface pushing water down underground, now you've got quite a head on there kind of injecting the water even without a pump at a much faster rate than it would have occurred under ordinary static conditions. So this is a great idea to try and encourage groundwater recharge. Now the risk is that if it's going to an aquifer that people rely on for drinking, now we've taken surface water discharge that may be contaminated with animal waste or with fertilizers or pesticides, and so we need to be cautious about where you inject drinking water relative to drinking water wells that are going to be extracting. And so hopefully, if this is a stratified aquifer, meaning that there are different depths at which water exists, and maybe they're confined by layers of really low hydraulic conductivity, maybe the drinking water well goes down 100 meters, and this is just going to more of a surface aquifer, and they're separated by a couple of layers of clay that would be reducing the rate of movement until bacteria in the soil could remove any microbial contamination, and hopefully there's no chemical pollution, although in Tamil Nadu there probably is a lot of pesticide use there. All right, so those were interesting videos, and they kind of set the stage for part of what we're going to be talking about today. Here's a cross-sectional view, and this is what I was just talking about, where you can have multiple aquifer layers, and so this kind of helps us to understand some of the important terminology. An aquifer is just where the voids are saturated with water. And so there can be water in the soil above the water table in the form of soil moisture. But when all of the voids are completely saturated with water, what that means is that we could extract the water out. Now, an aquiclude is where water is present but can't be easily extracted because of a low hydraulic conductivity. And so this cross-sectional impervious layer is meant to represent like a clay formation. And the confined aquifer has a confining layer above and below it. And the reason why it's pressurized, you can see from this well casing where the water is actually coming out without even having any kind of a pump. So that's showing that at sea, the aquifer is pressurized, is because the water table is perched. If you look over here, we've got rain onto a hillside that's elevated, and there's enough of the water over here that this is the free surface of water. Here's the water table, and we're going down. The pressure is increasing to the point of where through the soil there are some losses in pressure. You can see here the water table height is higher than it is there. And that tells us that the movement of the water is going to be from where the water is high to where the water is low. So it's moving from A towards B, towards C. But if you puncture this pressurized, confined aquifer at sea, then the water is going to come loose. And that's an artesian aquifer when it actually flows freely to the surface. Feel free to interject with any questions. We're going to look at several different representations of the subsurface today. An artesian aquifer, as I just mentioned, is where there's enough pressure underground that the water would actually bubble to the surface. And so it's a spring. A spring is an example of an artesian aquifer. An aquitard is some formation that slows the water's movement. You got a new insult now, right? And a leaky aquifer is one where it's semi-pervious, and so that could be fractured rock, or it could be a silt that has maybe reduced hydraulic conductivity but not extremely low hydraulic conductivity like a clay. And so in this case, think about if this lower confining layer had fractures through it, then it's possible that the water could be leaking through those fractures. There might be an unconfined aquifer underneath this confined one. There can be many different layers of confined and unconfined aquifer. And so that's the stratification of the subsurface. And ironically, the water can drip up too. It doesn't always just drip down. So it could be that there's enough pressure in this confined aquifer that the water could be leaking upward towards that unconfined aquifer. Darcy's law, which we've talked about on a couple of occasions already this semester, is important in understanding the movement of water in the subsurface. And so here's a good representation of Darcy's law that shows that the movement of water as a function of volumetric flow rate Q depends on the differential of the water pressure between the upstream end and the downstream end of some soil column. And we often will represent this as like a circular column of soil where the water is flowing from left to right. But in a three-dimensional underground environment, it's not quite as simple as that, because there isn't the impermeable casing around the soil matrix. Here the water is only moving in one direction. But down in the subsurface, it's not just moving in one direction. And so we have to be aware of that complicating factor. But here we have a delta H that is the driving force, some length between the two. And the Darcy's law says that there's a proportionality factor, the hydraulic conductivity K, that relates the cross-sectional area that the flow is traveling through the head ratio between the delta H and the length, and then the flow rate that we get. So K is key. It's important for us in a lot of the subsurface calculations that we're going to be doing. We're going to focus on wells today. And the reason why is because wells come up a lot in the FE exam, and also it's a good starting point for understanding the behavior of water in the subsurface. There are two main cases of water moving underground. One is with an unconfined aquifer that you're pumping from, and then there's also when you're pumping from a confined aquifer. So we're going to look at those two cases and work a couple of examples that tie into them. Now here, this is showing, here's a new bit of terminology, a cone of depression. That's another kind of, I think, a funny phrase, a cone of depression. I'm sure we've all felt the cone of depression towards the end of the semester as we realize we won't be sitting in class anymore and we've got a lengthy, annoying vacation ahead of us. But here, what causes this, okay, so here's the water surface. This line that's separating the light from the dark. So the light area represents where you've got saturated voids, and above it where it's dark is the soil that's unsaturated. So this decreasing line here is the water table. And so the water is moving in 3 dimensions. If we were to look from above, we would see that there's water coming from all directions towards this well. So this is just a single cross-sectional view. It's not that water is only coming from the right and is only coming from the left. It's that water is converging from all directions in a circular pattern towards that well because there is some sort of a pump that's extracting water from this well, and so it has to come from somewhere. And it gets into equilibrium. The bigger the discharge that you have, the larger this cone of depression will be, because it's the cone of depression that's the driving force that moves the water underground. Like, what brings the water towards this well casing so that the pump can take it out? The pump isn't sucking the water out of the soil. That's not the case at all. Actually, there is a free surface of water in the well casing, and so that's what this line represents, is that the pump is fully submerged in water, and it's pumping the water out, but something else is drawing the water towards the pump. And what it is what's drawing the water towards the pump is the drawdown. And so if you take a liter of water out of this well casing, then you've got a low point. You've reduced the height of the water table a little bit, and the water flows towards the location of low energy. Remember, water always flows downhill, whether it's in a pipe where you've got flow from high pressure to low pressure, or if it's in a creek bed, water is flowing from upstream to downstream because the upstream was higher elevation. And so here, the water is flowing from high elevation, where there's less drawdown, towards the pump, because in the well casing, you've got the lowest elevation of all. And so you get more depression with a greater flow rate. Yeah. What you working on, Andrew? Yeah? When's it due? Tonight? All right. This is important stuff. This will be on the final exam. Okay. So let's look at the role that different material types plays on different drawdowns that you might observe. So what this is showing is on the left, you've got a lot of drawdown, and on the right, you've got less. I love showing pictures and telling students, explain this to me. Tell me why there's less drawdown on the right. So based on what you know about drawdown and soil properties, how would you answer that question? Why is there less drawdown on the right? That's it, yes. So why can the water flow more easily? All right, so yeah, looking at the material type difference, coarse gravel versus fine sand. So the hydraulic conductivity of coarse gravel is going to be higher, And so what that means is the water is flowing more easily, and for the same flow rate, if we assume that in both of these cases the discharge is equal, you don't need as much drawdown to bring the water towards that central location from which it's being extracted. All right, so that's an important principle, is in the first picture that more flow rate gives you more drawdown. In the second group of pictures, that high hydraulic conductivity gives you less drawdown than low hydraulic conductivity. So you need a more extreme pressure, or I guess we'd say piezometric head difference, because the piezometric head is the shape of that drawdown. So here we need to have a really extensive drawdown to force the water through that fine void sand. Now if we have two wells that are both pumping in close proximity to each other, then the cone of depression can overlap, and actually it's an additive thing. If this well had been here by itself, the well on the left, A, well A, this is what the drawdown would have looked like if it was there by itself. But we also have well B in close proximity, and so there's drawdown from each of them, and so it kind of is going to increase the drawdown that both are experiencing. And so this is part of the issue in agricultural areas, is that everyone has big pumps. And so the drawdown isn't just from one farmer, but you have to worry about what the neighbor next to you is doing, and it gives you ever more incentive to be the man on the block with the biggest pump, is so that you can out-pump your neighbor, and so that your pump can go deeper, and when his well runs dry, yours doesn't, you know. You want to grab everything for yourself. All right, so a fully penetrating well would be a well where the casing is all the way through the depth of the aquifer. Let's go back to a picture really quickly. None of these wells are fully penetrating through the confined aquifer. If they were fully penetrating, then the well casing would go all the way down to the bottom, and they would be screened through the entire depth of the aquifer, meaning that water doesn't have to flow through just some of the depth, but water can flow through all of the depth towards that central location. So if we go back now to the terminology that we're looking at, okay, fully penetrating means all the way to the bottom. Screen depth, the screen are these slots in the drain, or sometimes it is like a physical wire mesh to try and keep the soil and rocks from going into the central location, where really all you want is the water to be there. And the well radius is actually talking about the radius of the physical pipe itself. And that's one of the parameters that we're going to put into the formulas that tell us how much water you can get out of a well for a certain drawdown. Now you all know about hydraulic conductivity. There's a closely related term that takes into account how thick the aquifer is, and that's transmissivity. And for a confined aquifer, we would have the height of the aquifer B multiplied by the hydraulic conductivity to get the transmissivity. But in an unconfined aquifer, we'd just use H, which is the depth of the water from the bottom of the confining layer in the unconfined aquifer up to the water height itself. And so H is basically just how deep the water is inside the unconfined aquifer. Okay, so hydraulic conductivity has units of length per time, whether it's centimeters per second or meters per day. It's just a measurement of how easily water flows through the soil, and it's affected by not only the void size, but then also it's affected by how attracted the material is to water. And part of the reason why clay has such a low hydraulic conductivity, of course, is because of the negative charge of clay particles. And so there's an attraction between the negative charge on the clay particles and the positive charge that exists in an oxygen. In water molecule H2O, we know that the electrons go towards the hydrogen, and so You know, it's a polar water molecule, and that sort of accounts for the slow movement of water through the clay soil. Aquifer thickness, B. Transmissivity, piezometric head is pressure divided by gamma plus elevation. And piezometric head is going to tell us how much energy is available to drive the water towards the well casing. And then one last term that we haven't talked about today, but we have in the past, is the effective porosity. And of course, porosity is just a measure of the voids in a soil matrix relative to the overall volume. But some of those voids may not be interconnected, and so the effective porosity takes that into account, as well as some of the void is full of water that can't actually be removed because it's so closely bonded to the surface of the soil grains. And so effective porosity is accounting for both of those factors. Okay, this is what we've been working up to. Here's the formula that allows us to relate for a confined aquifer. The confined aquifer is the simple case. The unconfined aquifer we have to make a slight adjustment to. But here for a confined aquifer, B is the thickness of the aquifer from the lower confining layer, between the lower confining layer and the top confining layer. Now here you'll notice that this is a fully penetrating well, and the diagram is showing that it's screened. The entire depth of the aquifer is screened. And so the water is just going to be moving horizontally towards that screen so that it can enter the well casing and be pumped out. Now what this is saying is that we need to know the transmissivity, T, so that, remember, is B, which is the height of the aquifer multiplied by the hydraulic conductivity. H1 and H2 is the depth of the water at some locations away from the well. 1, by definition, is the location that's closer to the well, and 2 is further away. So there's a convention there that we have to keep track of. Other things will go awry. And the interesting thing about the way that these well equations work, by the way, have you seen these well equations before? Have you done problems like this? All right, good. So this isn't the first time you've seen it. So location 1 can be the pipe itself. You can use that as location 1, and in that case, then you just use the depth of the water. For a confined aquifer, this is how it looks in the supplied reference manual for the FE exam. This is the equations that they've provided, and they call it the theme equation. I guess I after E would be pronounced thime equation. Let's get some practice with that, just to dust out the cobwebs and get some practice crunching the numbers here. We've got a hydraulic conductivity of 20 meters per day. The thickness B of the aquifer is 6.6, and the initial piezometric surface of 14.53 meters above the lower confining layer. So that means that before pumping, H, capital H, is 14.53 meters. So we want to know what's the Q that's going to cause the piezometric surface to be at 13.85. So you're going to have to use that as the H value. And one thing I should point out is that we've been talking about the cone of depression, and a related term to cone of depression is drawdown. You know, drawdown is the distance between where the water used to be, or where the water is when pumping doesn't occur, and when pumping is going on, and where the water level is. And so drawdown is the difference between those two. Sometimes the distractors in the FE exam are trying to trick you into substituting drawdowns for the actual H values, which is supposed to go into the equation. So don't fall into the trap. Know the difference between the piezometric depth and the drawdown. So here, we've got a two-part question. What's the flow rate that would cause the surface to be under these conditions at the two radiuses that are given, and then what's the water depth in the well if we've got a well diameter of 0.5 meters? So I'm going to pause the recording, give you some time to plug and chug, and then we'll look and see if we're all on the same track. Okay, here's my solution up on the screen there, showing that we should get a flow rate of 506 cubic meters per day in order to see the heights of the water surfaces that are described in the problem statement at the different radiuses. So then the second part of the problem, you need to use a new R1, and the R2 that you use can either be the 40-meter location or the 85-meter location. Either one is okay, as long as you use the correct height of the water surface at that spot. So I won't show you the solution to the second part quite yet, but just to confirm you're headed in the right direction, there's the first part of this confined aquifer problem. Okay, for the second part, we want to find out what's the depth at the well under these conditions. So essentially, we're just going to be solving for H1 given an R1 of 0.25. The same flow rate, the same hydraulic conductivity. You need to pick a location too. So are you going to use the radius out to 85 meters or the 40-meter location? In my solution, what I did was I said, okay, so R1 is going to be 0.25 because that's at the well itself. And I let the location 2 be the closer monitoring well, where we're keeping track of the water elevation 40 meters from our extraction well. And the height of the water at that monitoring well 40 meters away is 13.85 meters. And so for that same flow rate then, it tells us the depth at the well itself should be 10.75 meters. Anybody else get that same water depth? All right, good. These problems are hard to write because you can create problems like this where it becomes like an impossible, like the output number is impossible. So writing well problems is sometimes an iterative process to make sure that it works out and then it's not negative flow rates or negative water depths and things like that. All right, well, so that is a confined aquifer, which is the easy case. Things are just a little bit different for unconfined aquifer. You have to calculate an H, you have to square essentially the depth of water rather than it was just the depth of water in the case of a confined aquifer. Some texts, instead of squaring it, have you calculate like a modified or an effective height. If we look here in the FE reference manual, Dupuy's formula is squaring it. That's how they have it in the reference manual. And so let's take that formula and try it out here. We have an unconfined aquifer where we are given the flow rate, 0.4 cubic meters per second is extracted from this unconfined aquifer. And the saturated thickness is 24 meters. So that's this depth H. That's how high the water level is before there's pumping. So now this is expressing the heights of the water in terms of drawdown. So 50 meters away, there's a meter of drawdown, which means then that the H is going to be 23 meters at that location. And 100 meters away, the drawdown is 0.5 meters. So you can use that, first of all, to calculate the hydraulic conductivity, and then in part B, I'd like you to calculate the drawdown 5 meters from the well. Interpreting the problem statement is more than half the battle on these. I mean, just trying to figure out what it's asking and not confusing drawdown with head and that sort of thing. Okay, so this is showing the first one. I guess maybe 80 would be. So we can rearrange the equation for k and making sure that the units are consistent with what we ultimately want. You know, if the k value is going to be in terms of meters per second, then we'd want to take the flow rate, which maybe would be given in meters per cubic meters per day, and convert it. But in this case, we also are calculating the h values from the given drawdowns. Okay, so 3.8 times 10 to the minus 3 meters per second is the hydraulic conductivity of that material. Has anybody already calculated the drawdown? Okay, let's take a look at that part too. Okay, I've got 2.74. I don't know why it's not on the screen there. I have it on my paper. I guess I didn't scan the entirety. That's funny. All right. 2.74 meters. Okay, well, great. You're just rearranging the equation again for R1 is 5 meters, H1 is unknown. And so the H1 that you'll solve for should be 21.26 meters. And then once you have 21.26 is H1, then capital H of 24. So 24 minus the 21.26 is 2.74. And that's the end of the semester, guys. But course evaluations, only 3 of 9 have completed the course evaluations. And so what I'm going to ask you to do is use the remaining 60 seconds of our class time to get out your phone or go onto the laptop to mymu.marshall.edu in the Student tab, then Student Resources, Course Eval, and write your evaluation for the course because, yes, to the solution. Yeah, I'm going to open it again. This one? All right. Okay, so yes, please, your evaluation. It's important. Even if the 3 people who responded already said great things, it just doesn't look good if only 3 of 9 filled out the course evaluations. It makes it look like you don't care, and I know you do care.